Hello, in this video we will look at how to calculate the binomial probabilities using the Ti-83 or Ti-84 graphic calculator. There are 4 examples here. We'll also talk about the mean and standard deviation for a binomial experiment. So let's get started. In the opening examples in the notes for a class, there are examples of binomial probabilities. Here is example 4.10. It says a fair coin is tossed 10 times. We want to calculate the probability of getting exactly 3 tails in 10 tosses. In order for us to calculate binomial probabilities, using the calculator we need to have 3 things. The first thing we need to have is a fixed number of trials. In this case, the number of trials is 10 because we are tossing a coin 10 times. We need these trials to be independent, which they are. The outcome of one coin toss does not affect the outcome of a second coin toss. And we need the probabilities to be the same. In this case, the probability of getting a tails on any one coin toss is 50%. For part A, we want to get exactly 3 tails, so we're looking for x to be 3. So in the Ti-83-84, we're going to use the distribution function, which is just above vars. To access it, we'll hit second vars or variables to pull up the distribution. And we're looking for binomial PDF. In my calculator, I have to scroll all the way down until I get to A. But there's a much faster way of getting to this. Instead, I could just hit alpha math, which will access the green letter A and pull up binomial PDF for us. Much faster way of getting there. So the number of trials is 10. The probability of success is 0.5. And the number of successes we want is 3. And we get this. If you are using the Ti-83 or if your calculator does not have the update to look like mine, then you just need to type in 10, use the comma button, which is above the 7, 0.5, comma, and 3. It needs to be in that order. The order is important for these. And we'll get the probability of 3 tails in 10 tosses to be 0.1172. For probabilities, we're going to round to 4 decimal places unless we're told otherwise. Now, for the second part of this question, it says, what is the probability of getting at most 1 tail? Well, at most 1 means getting 1 or less. So this means getting either 0 or 1 tails. So there is another way of doing this in one step using what's called the cumulative probability, but we're not going to worry about that for right now. We'll just look at how we can enter these values into our calculator. So binomial PDF, going to access it the same way. We're going to hit second vars, hit alpha A. We want to change this to now have an x value of 0. And we can find the probability of getting 0 tails. So the probability of getting 0 tails is What? Well, we have 9.7656 E-4. Well, this is scientific notation, and it says that we need to move the decimal place 4 places to the left. So we would have 1, 2, 3 zeros. So again, if we wanted to round this to 4 place values, well, this would be 0.0010, because the 9 would get rounded up by the 7, and it become 1/1000th. All right, so now there's a faster way of entering these repeatedly into the calculator. Another way I could do this is just by pressing second enter, and it'll re-enter exactly what we have, and now we can just change it to 1 tail, the probability of getting 1 tail. And that would be 0.0098. Again, 4 place values, the 6 rounds the 7 up to an 8, and we can add these 2 together. When we add these 2 together, oops, sorry about that. Well, we can add these 2 right in the calculator. We will get the answer to the question at most one tail, and that would be 0.0108, because again, the 6 rounds the 7 up. At this point, I would encourage you to pause the video and try the calculations that I was just working on and confirm that they work. We also have example 4.12 from class. According to a Gallup poll, 60% of American adults prefer saving over spending. Let X equal the number of American adults out of a random sample of 50 who prefer saving to spending. So is this a binomial experiment? Can we apply the binomial probability distribution to it? Do we have a fixed number of trials? Yes. What is that fixed number of trials? 50. Are the trials independent? Independent. Yes. The fact that, I don't know, person A prefers to spend does not affect whether or not person B prefers to spend or save. And are there only two outcomes? Yes, either the person spends or does not spend, or saves or does not save. So what is a success for this experiment? Well, they say in the question, the number of people out of 50 who prefer saving to spending. If a person prefers to save, that is a success. So what is the value of P then? What is the probability of success? Well, according to the first sentence, 60% of American adults prefer saving. So 0.6, because 60% of adults prefer to save. Now we're going to use our calculator to calculate the following probabilities. Find the probability that 25 adults in the sample prefer saving over spending. So for this one, we have N is equal to 50, P is equal to 0.6, X is equal to 25. I suggest pausing your video now and trying to calculate this. All right, do you have an answer? Let's look to see how to do this in the calculator. Second vars, alpha A. We now have 50 people in a sample. The probability of success is 0.6, and the number of successes we are looking for is 25. Press enter, and we get the probability that X equals 25 is 0.0405. Again, rounding to 4 decimal places. Not too bad. Now, part B says the probability that at most 20 adults prefer saving. Well, what does at most 20 mean? At most 20 means, I guess, less than or equal to 20. So that would mean 0 adults prefer saving, 1 adult prefer saving, 2 adults prefer saving, 3 adults prefer saving, so on and so forth. In the previous example, when we had at most 1 tail, well, that was easy because we said just 0 or 1. We just calculated those two separately. Now, if we have at most 20, well, that means a whole lot more than 0 or 1. So we can use the cumulative binomial probability distribution. If the question asks for up to and including X, as it does here, not in the exact same words, but at most 20 is the same thing as up to and including 20, then we can use the cumulative binomial probability distribution. The cumulative in the Ti-84 is the binom CDF. So I did not show this before, but if we go to second vars, and an easier way to find these is to scroll up. There's just less options to scroll up. And we'll see that the B option is binom CDF. This is for a cumulative distribution, again, looking for up to and including x. If we press enter here, it looks basically the same. The only real difference is, if you look where my cursor is on my calculator screen, we're looking for the C, not the P. So in this case, we're going to enter 50 trials because we still have 50 American adults. The probability that they prefer saving is 0.6, and we're looking for the maximum value to be 20, up to and including 20. And this will find the cumulative probability. So this will find the probability that we have x is equal to 0 plus x is equal to 1 plus x is equal to 20. I'll show a better representation of this in a second. Let me just copy down the answer, again, to 4 place values. So another way of thinking about these up to and including probabilities is to think about them as a binomial distribution, meaning a table. So if we have 50 American adults, we could have 0 that prefers saving, or 1 that prefers saving, or 2 that prefers saving, or 19 that prefers saving, or 20 that prefer saving, or 21 that prefer saving, or 49 that prefer saving, or 50 that prefer saving. These are, again, the number of American adults in the random sample who prefer saving over spending. The way that we would find any one of these probabilities would be with the binom PDF. So we could find 0 by doing number of trials is 50, probability that they prefer saving is 0.6, we want 0 of them, and we could find those individual probabilities. What we just did with the binomial CDF is we found the cumulative probability, the cumulative probabilities, I'm just going to leave it as prob, for x equals 0 to x equals 20 in one fell swoop. So the binom CDF for what we just calculated will calculate all of the probabilities between 0 and 20 and add them all together. That's why we call it a cumulative probability. All right, the last part of this question asks us to calculate the mean and the standard deviation. Since this is a binomial experiment, we only have 2 outcomes. The mean is the expected value. We would just do 50 times 0.6. 50 times 0.6 would be 30. I can show that really quickly. 50 times 0.6. So we would expect 30 American adults to prefer saving. Expected number of adults who prefer to save. And the standard deviation would be the square root of 50 times 0.6 times 0.4, which we can do in the calculator as the square root of 50 times 0.6 times 0.4. And we will get that the standard deviation is 3.46. Note that both of these are population values. They're population values because we're trying to predict the outcomes for all future experiments. All right, then there's another example here, example 4.13. It says a fair 6-sided die is rolled 10 times. Each roll is independent. You want to find the probability of rolling a 1 exactly 3 times. All right, so this one is a little bit tricky because when we roll a die, there are 6 outcomes because it's a 6-sided die. If we were to just ask the question, what are the outcomes of rolling a 6-sided die, we would not consider that a binomial experiment because there are 6 outcomes. However, if we are looking for a 1, we now have a binomial experiment. So the number of rolls would be 10, because we're rolling the die 10 times. The probability of rolling a 1 would be 1 out of 6. We're looking for exactly 3 1s. So we can do this. In the Ti-83-84, we're going to do binomial PDF of, let me move this down a little bit so it doesn't interfere, of 10 rolls with a probability of success of 1/6, where we have 3 successes. Let me clear my calculator screen. We can hit second vars, alpha math, 10 trials. The probability of success is 1/6. We could type that in right as a fraction, and the x value is 3. Hit paste, enter, and we get 0.1550. We don't really need the 0, but I'll put it in there just in case. All right, so that's how we calculate binomial probabilities, both for exact values and for cumulative values. The one thing I did not show earlier was how to get to the binomial CDF quickly. If we wanted to get to the binomial CDF quickly, we could hit second vars and then hit alpha B, which is above apps. So again, if we wanted to do this, we quit, clear, hit second vars. We can hit alpha A for binom PDF. We use binom PDF for exact calculations, as we just did with example 4.13. And we can get to the cumulative probability binom CDF by using alpha B. And we would use those for calculating the probability of up to and including a certain outcome.